Sounds good. Thank you so much for the intro, and thanks for having me. I'm excited to be here and tell you a little bit more about our work. As Nate already mentioned, we work at the interface of applied mathematics and earth science, and a lot of what we do is think about how can we write models, how can we use models in a more strategic and a more efficient way to both advance our understanding of Earth, but also to reduce risk for communities, for people, for other species that might be associated with extreme events. So today I want to present to you, give you a bit of an overview for one of our projects, which is focused particularly on ice sheet dynamics. So my talk is entitled The Causes and Consequences of the Large Uncertainty in Near-Term Sea Level Rise. And I think this is one of my favorite projects at the moment because I think it's such an interesting modeling challenge of how do we get at sea level rise. Clearly, it's an important question, but also so difficult to get at. So let's think a little bit about this. As Nate already said, my group actually works quite broadly on extreme events. And the key idea here is that I feel like many of the fundamental physical processes that create these extreme shifts in behavior are actually quite similar between different natural systems. So we're really trying to understand the fundamental physics behind these extreme shifts in behavior. And also we try to develop models specifically that leverage different data sets. So this is there's a lot of excitement about big data at the moment. This is really a poor data problem. We don't really have great data on volcanic eruptions or on ice sheet disintegration, mostly because those events happened either way in the past or because we can't instrument these kinds of events. So it's really a poor data problem. So a lot of our models are focused on trying to leverage specific data sets that we have more intentionally to advance our understanding. So I spoke about the large uncertainty in sea level rise. Let's maybe, for those of you who don't regularly think about sea level rise, let's sort of make that more specific. So here are some figures that were recently published in a report, Rising Seas in California. That was in 2017. I want to emphasize that I do not defend these models. I'm just kind of showing this as an FYI. This is some of the things that I think the stakeholders we work with worry about. So what you see here on top is global mean sea level. What you see at the bottom is the relative mean sea level in San Francisco Bay. And the bottom line, or the key takeaway from these graphs, is really that there's a bunch of models. There's the historic data, which ends, which obviously ends in the year that this figure was produced. And then there's the RCP type models, which are the ones from the Intergovernmental Panel on Climate Change. So these are models that really look very broad scale at the CO2 concentration in the atmosphere and how that affects climate change. And then there's this H++ model. And you might notice right away that the H++ model does not have a number associated with it in the legend, which means that does not actually depend on CO2. So what's so different about H++? H++ is a model that tries to take into account the ice sheet dynamics, particularly sort of the potential instability of parts of the Antarctic ice sheet. And that's also why it gives such a hugely bigger estimate than the other two. So the way to think about these models, I would argue, is really that they map out a range of possible scenarios. And I think H++ was sort of intentionally designed to just kind of show the potential of rapid ice loss and just kind of get that debate started. But I think all of these models are ultimately not actually intended to look at sea level rise itself. So what do I mean by that? And what do these models exactly do? Since, we care deeply about models, I hope all of you do. So let's think about what these models actually do. So here is a brief overview of ice sheet models. So on top, you see sort of a schematic of an ice sheet where I have snow being deposited on top, building up the ice sheet. Then the gravity forces the ice to gradually flow towards the ocean. In that process, I lose some meltwater at the base, and I'm creating a flow field in the ice. And then I'm also losing ice through QC, which is the flux of the ice into the ocean. And that's typically what I care about when I look at sea level rise. Now, how do we model that? Most ice sheet models that exist use some variant of these equations that you see here, usually more simplified than the ones here. So the first one is a mass balance of the ice. So I'm looking at the evolution of the height of ice as it flows towards the ocean and loses water at the base and gets snow on top. The second one is a force balance. And interestingly, sort of when you look historically at how glaciers have been modeled, initially there was a huge debate over, is a glacier more like a mountain and it fractures, or is it more like a fluid and it flows? And that tension was never resolved. But interestingly, the ice sheet models just kind of took the fluid point of view and ran with it. And I think that decision, or that assumption, still haunts us a little bit today, where most of these models really look at the timescale of flow. And why is that an issue? Because, of course, the viscosity of ice is 10 to the 14 Pascal seconds. So this ice is moving very, very slowly. And then we have a couple of boundary conditions. We have the free surface condition, and we have the basal conditions. Now, what is exactly the question that these models are asking? As I already mentioned, they are really looking at a mass balance of the ice, right? The only time scale that appears in these models really comes from the mass balance part. Now, that is a choice, and it's actually a rather important choice, and also a consequential one. So I would argue the question that these models really ask is not about near-term sea level rise, because when these models were first developed, the questions that we were thinking about in the scientific community was really, are the ice sheets even a problem, right, from a climate point of view? Because as you could imagine, because ice flows so slowly, it might not necessarily expect the ice sheets to be a big contributor to sea level rise, because the motion is just really slow on the time scales that we care about, which is decades. So over thousands of years, these ice sheets might not do all that much. So these early ice sheet models, I think, really ask the question, how do temporal changes in the mass balance affect ice flow? But that's slightly different than what we're interested in today. So today, we're really asking a different question. We want to know, what is sea level rise going to be by 2050, by 2060, in the next 2-3 decades, which is quite different. And at this point, I think it is worth mentioning that there actually are a number of embedded timescales here that we don't usually worry about. So for example, at the base, how fast am I losing water? That's the question mark over the AB term, the part where the basal meltwater gets removed from the ice. And how does the stress at the base change over time? That's the tau B. Does it change only in magnitude, or maybe even the functional relationship between the stress and the flow speed of the ice will change fundamentally? Capital N in this equation is the effective pressure of the meltwater at the base. That's very important, both for lubricational siding, but also for other hydrological behavior. How does that change? How is the water pressure going to change, right? So these are, I think, subtle differences, but very important differences, because of course the viscosity of water is 10 to the minus 5 Pascal seconds. In other words, water moves 19 orders of magnitude faster than ice. So if I'm interested in fast change, it often is useful to look at the fast moving phase, which in this case is not ice, but is water. So the first thing to realize is that when I'm interested in fast and rapid change, slip is faster than flow, right? So this again comes to this decision that ice sheet models made to focus on the flow aspect of ice rather than the slip aspect of ice. But slip is so much faster. So how fast can ice flow? Well, here is a picture from a glacier that a friend of mine took, and you can see how we think about flow of ice and what we mean by that. So on the left figure, you see some nails hammered into ice, and you have a little yellow tape for scale. And then if you come back a year later, all of these nails in the ice have moved a teeny bit. And you see something that almost like starts resembling a parabolic flow profile. So that is what we mean by ice can flow. It can flow in the sense that it gradually, like the deformation occurs gradually within the entire ice layer. And that's for a long time how we thought about ice sheet dynamics. But is it true? So here is a bunch of data that I think have very fundamentally changed the way we think about ice sheet dynamics. So when you know nothing about ice sheets, and like only a few decades ago, I think we barely knew anything about ice sheets. The first idea you might have is that, Antarctica is essentially a huge ice cube. So let's model it that way, right? Like I have basically a huge ice cube sitting in water. And as we all know from, say, the ice cube in your water at lunch, these ice cubes would melt from the outside in. So they gradually get eaten away at the edges. What you see in this image is the opposite behavior, where we see ice being drained very rapidly from basically the center of Antarctica. So these are these red drainage routes that you're looking at here. Note that the speed scale is logarithmic. So in the blue zones, the ice is moving at about 1 meter per year. So that's kind of similar to what you just saw in the glacier image. But in the red zones, the ice can move up to 3 orders of magnitude faster than that. So that's a huge change. And that I think has fundamentally sort of revised our way of thinking about Antarctica, where now I think we're beginning to realize that Antarctica is actually melting from the inside out through these very rapid drainage pathways that are called ice streams and sometimes glaciers that transport this ice very rapidly to the ocean. So what is the black line here? The black line is also very important here. The black line is the so-called grounding zone. It shows where the ice loses contact with the bed. So for most of Antarctica, most of West Antarctica, the ice sits on a weak sediment, and as it moves over the weak sediment, it rubs against the weak sediment. But at this black line, it loses contact with the sediment and just kind of starts floating. So what creates this really curious behavior that ice is moving 3-4 orders more rapidly than we thought it could, and we thought it could based from a fluid flow point of view? Let's focus on this area here, which is the Suckale Coast, and for scale, I've added New Hampshire on top of one of these ice streams. So these are very significant flow features. These are not minor trickles. These are huge motions of ice, and this ice is slipping. It is not flowing. So this ice is basically slipping as a huge block toward the ocean, and that creates the behavior. Now, why is this area interesting, and why has so much work been focused on this area? The reason is twofold. For one, our prediction of sea level rise depend very sensitively on these drainage routes. So these red drainage routes you see here contribute 90% of the ice loss from Antarctica and the sea level rise contribution of Antarctica. Now, the question, of course, is, are these going to remain where they are? Are these going to stay constant over time or not? And here in the Suckale Coast area, if you look very closely at the image in the lower left, you see that there actually is a blue gap in the middle, in which the ice stream here stopped moving. So you can see that there's still tributaries, right? And then there's sort of this big blue gap. So there used to be an ice stream here about 200, 300 years ago, and it stopped moving. It just disappeared into nothingness, and we don't quite know why. So there's been a lot of concern around these ice streams potentially moving in location, changing in width, or accelerating.
Hey, Dr. Suckale, we had a question pop up in the chat. Lekan, would you like to ask?
Yeah, I was just wondering how you determine the speed. Is it a measurement or through a model?
That is a measurement. So this data is remote sensing data, right? So this is satellite data. So the satellites basically look at little tracers on the ice and see how fast they move. So this is all observational data. And this is sort of like the observational data that, really, I think, triggered a revolution in how we think about ice sheets. Does that make sense?
Yeah, thanks.
All right. But there is another interesting piece of data here, which is looking not at the ice on top, but is looking at the subsurface. So if I show you again sort of the figure on the left and bottom, so if you look at the left bottom and I just peel away the ice speed, that what you're looking at now is basically the subsurface. And this is through ice penetrating radar, which is sort of another observational technique. It's usually with little planes that fly over the ice, or also instruments on the ice itself. But it's basically radar that penetrates down to the bottom of the ice and gives us a reflection, so we can understand what the subsurface looks like. Why am I showing this? Well, the key reason I'm showing this is that you can no longer see the ice streams, right? So that's the important difference between ice streams and glaciers, is that for ice streams, I do not know where they are based on the basal topography. Glaciers typically go through some sort of mountain valley, right? So the topography basically defines the location. For ice streams, that's not true anymore. So ice streams could basically have no clear correlation to topography typically. Now, why does that matter? Well, it matters because the discharge now becomes very unstable. So on the left-hand side, you have an outlet glacier where the discharge is basically scaling with velocity. On the right-hand side, you have these ice streams, which are really puzzling features once you think about it, right? Because you have these huge chunks of ice that kind of slide down a plane. So why do I have them move 3 orders of magnitude in one area and not in the other, right? Like, it's really a puzzling observation. And what's more is that the force balance of these, if I were to disturb them a little bit, right? So if you did, like, say, a stability analysis on this, and you just perturb them in width, then you need to balance more gravity, right? Like you need to balance more gravitational stress. The gravitational stress scales with width. But the basal stress wouldn't, right? Like the basal stress is just the properties of the sediment. That would not give you a factor that increases with width at all. And in fact, on the edges where I have these sort of crevassed margins, that's where I get some lateral stability, but also that wouldn't increase with width. So the concern with these ice streams when it comes to sea level rise is really that if one of these ice streams were to move or were to change in speed very dramatically, then I could get a hugely different estimate for sea level rise, because these are such dynamic features and we know in the past that they have been dynamics. The problem is we don't really understand what governs the physics of these ice streams, and that's something we would really like to find out. So the interesting insight, I think, from this kind of thinking about ice streams, and particularly from the data we have, is that it's really about the motion of the margin, right? Like this is really a problem which looks at how stable is this margin and how would this margin move? And of course, this is not just the case here, but you can look at where are these margins. So I've replotted in this slide, I've just replotted the speed data in terms of shear strain rate. And you can see the arteries of this Antarctica heart a lot more clearly now, right? So like these blue and red zones are really what I care about. And what's important to note here from a sea level rise point of view is that if you care about sea level rise, right, like you really care about land ice, we don't really care about the shelf. So if you look at the left again, if you're further to the ocean than the black line, the ice is floating. So this ice, if it breaks away, it doesn't actually change sea level rise because it's isostatically compensated to start with. The big factor when it comes to sea level rise is really the land ice. So that's the part in the ground, the ice that goes over the sediments, over the grounded portion of the ice sheet. So with that, I think we can reduce the question we started with, which is, where does this uncertainty in sea level rise come from? Really to how will land ice sliding, note the sliding, not the flow. So we're really interested in sliding here. And how does this sliding respond to melting at the ice-ocean interface? The ocean still perturbs the ice sheet in a very significant way, just like for your ice cube in the water bottle, but it perturbs it in a very different way. And of course, the key game changer here is the presence of sediment, right? Like the key sort of missing piece when you think about Antarctica as an ice cube is the sediments play a huge role. And so let's think about that a little bit more. And let's start with a very simple force balance, which I think is always such a good place to start. And so we've sort of identified our first sub-question, which is, can ice stream location and width change on a decadal timescale? Like, can it be that quickly, right? Because we really want to answer the question of like, what is sea level rise going to look like in 2050? So let's start with a very simple force balance. Here you look at a vastly simplified ice stream, which is just like a linear chunk of ice sliding down. So that's the stream. It is sliding because the sediment underneath it are failing, right? So like notice how the way we're thinking about this now is no longer as an ice cube. Here we're really thinking about the ice just as a mirror of what happens in the subsurface. So really this is just the subsurface creating trouble and the ice conveying that to the surface. So underneath the flowing ice, these weak sediments are failing. And so they don't provide enough resistance and the ice just slides down. On the ridges, they're still locked, right? So that's our ice stream. It's the driving force is gravity, the resisting force is the basal stress, and then I also have the lateral stresses. Now, if you look at the measurements, typically I actually need the lateral stresses for this to balance. That's not true for all ice streams. Some ice streams are balanced by basal stress alone, but many need this lateral stress. So if you just sort of try to balance this, you will see that the lateral stress scales with height, while the other two stresses scale with width. What does that mean? When you use Glenn's law, which is a way of thinking about the rheology of ice, so ice is a nonlinear fluid, I can plug that in for the average stress in the margin, and then I can compute shear heating in the margin. Shear heating is this tau epsilon dot term that basically tells you, because I have a lot of shear in these lateral margins, I'm going to create heat. Now, the issue with ice is, as ice gets warm, it gets weak, right? Like that's why ice cream is so delicious. Ice is actually very interesting in the sense that it maintains its material strength to a surprising degree in the vicinity of the melting point. For ice sheets, that's kind of bad news because this shear heating will scale as width over height to the 4th power because of Glen's law. Glen's law gives you the 3rd power here, like the 3, and the 1 you get from just sort of looking at the lateral versus gravity and basal stresses in the force balance. So this scaling would then suggest that I have a runaway situation potentially at hand, right? Where like a little width change will create a huge amount more shear heating, which leads to weakening of the lateral stresses. So the margins get weaker and weaker the more I widen. And at some point, these will just run away, right? Like in other words, this model would predict that these ice streams should eat away all of Antarctica, which clearly is not happening because yes, there have been some changes in ice stream locations, but they're not eating up everything, right? So what does that tell us? That tells us we've neglected a really important process in our model. So let's go to the next model. Let's go to model 2.1 or 2.0 and see what have we forgotten? Like what have we forgotten that creates this disconnect between nature and the model? And the key answer is, I think we've forgotten water, right? So like we've forgotten temperature, looking at temperature more clearly. So this is a model that one of my former graduate students wrote, in which we are kind of coupling a mechanical and a thermal model. And the mechanical model has a transition from slip to no slip at this shear margin. So at this lateral edge of the slipping zone. And the thermal model has the transition from tempered to frozen. So maybe the process that stabilizes the shear margin is freezing, right? Like maybe these ridges are just frozen to the ground. So the sediments can't fail because they're frozen into the ice. So that's been an idea that's been around for a while in the glaciologic community, that these margins are really a transition from temperate to frozen, which would then stabilize the margin dynamics. So we're going to test this model against Willen ice stream, which is one of the ice streams from the Cyprus coast that you saw earlier. And this specifically is the location that we're looking at here for Binchatter and also for Willen's. By the way, if you look at the right-hand figure, you see this blue blob again. This blue blob is Cam ice stream. So Cam ice stream is the ice stream that disappeared. So with our model, it's a free boundary model. So the strength of it is that I can understand the dynamics of these transition points from slip to no slip and from temperate to frozen. So what does that give me? The first thing it gives me is when I try to match this data, right? So like we are writing mostly forward models, and but then we test these forward models against the data. So if we test our models against the data, you can see the data suggests a pretty dramatic sharpening of the speed profile. So the middle figure shows you sort of the velocity or the speed, the downstream speed across different profiles that are shown on the left. So if you go from A to F, you're going downstream and the margin becomes sharper and sharper, right? Like this transition from slip to no slip becomes narrower and narrower. And our model would suggest that yes, for the first two, I might actually have the temperate to frozen transition coinciding with the mechanical transition, but not for the ones further down. Why not? Because this is basically a singularity, right? Like the transition from slip to no slip is a singularity. It's an integrable singularity, so I can handle it, but it's still a singularity and it creates a lot of heat, it creates a lot of stress. So the problem, in my opinion, with this idea that the frozen to temperate transition might explain shear margin positions is that I need heating. I need freezing in the location where I have the most heating. So that's kind of a problem, right? Like physically, that it doesn't tend to work. Certainly not if I have fast enough moving ice. So that slide kind of summarizes that as I go from this profile A upstream to profile F downstream, I sort of lose the connection between these two transition points, right? Which shows that we probably didn't get it right? Like, so we need to go back to the drawing board and come up with model 3.0 to think about this, right? Like, so the frozen to temperate transition works upstream, but it doesn't work so well downstream. Interestingly, these model runs actually gave us a clue for what might be happening. So when you look at the middle figures, you can see this red line, which gradually becomes steeper and steeper. So really, I have two interesting observations here. One is that at some point around profile CD, so around the transition between profile C and D, I actually reached the melting point in the ice. And that's highlighted by this orangey zone. That's why I reached the melting point in the ice. That doesn't mean I have a lot of water. right? Like this is just, I'm transitioning to ice cream in that area, right? Like I start to have a little bit of interstitial water in the ice, right? So like 1% maybe, not much, but it weakens the ice dramatically. And I might have that water seeping through the ice because of course water is heavier than ice, so it would tend to go to the bottom. And then it changes how the sediments behave. So let's think a little bit about that, given that we got a clue from this model, which is that probably water is important. Why would water be important? So here is model 3.0. We still have our simple ice stream. We still have the mechanical model. We still have the temperate model. The piece that we've added here is kind of shown on top as this interstitial layer of hydrology. I have water routing in this at this interface. And this water might flow as a film, but when you actually do a linear stability analysis on this film becomes unstable pretty quickly. So it's more likely that water flows through these tiny channels. Why does that matter? Because if I have water flow in a channel between the ice and the sediment, that channel would have a lower pressure. So it sucks in the water from the surrounding sediment. Now, one of the very interesting things we found by doing laboratory experiments on these subglacial tilts is that the strength of the sediment depends dramatically on water content, which is very common for dense granular media, right? Like that's the reason why like you can build sandcastles, right? Like by changing the water content in sand, I can go from an amorphous granular pile to an intricate sandcastle that holds all of these, funky shapes to something that is basically a water slush, right? So like water is incredibly consequential for the strength of the sediment. So what we're seeing here and what we're looking at here is, suppose I have a channel in this margin, which could come from the meltwater I'm creating in the margin. So that meltwater would then go into this channel, flow there, create a low pressure zone that drags in water from the rest of the sediment, which gives me a distribution of basal strength of the type you see at the bottom right, which is exactly the kind of strengthening I need to stabilize these kinds of ice streams. So the nice thing about this process is, A, it explains where the water goes, and B, it could be a process for identifying what stabilizes or what impedes the eat-away motion of these ice streams. So what impedes this unlimited widening? How does that work? Well, the stabilizing feedback loop would be, I'm going from a width change into creating so much water that now I start creating this channel, right? Like this channel is sort of the yellow dot here. Like actually the channel is a little blue dot on the bottom right. The yellow dot is the piece where I'm locking. But if I create this channel and I alter the hydrology, with that I alter the basal strength, and I'm actually increasing the basal resistance exactly in the area where I need it, because that's where I'm drawing out the water. Now that's an interesting idea, right? But, we need to test the model, right? Like at this point, this is just an idea. So is there any evidence that this might actually be true? And here comes Kim in again. So here is Kim, the ice stream that disappeared. And what you see here is data, not from us, but from Ginny Catania and a bunch of field missions that looked at ice penetrating radar for this area. So the idea with ice penetrating radar is, because the shear margins are very heavily crevassed, I can actually detect them even once they've been buried. So even if the shear margin is no longer visible on the surface, I can pick up on it because it creates such a strong reflector inside the ice, because the crevassing obviously doesn't heal, right? Like the crevassing stays there and gives me a sharp reflector. So this is just data that, that we're summarizing here, which posited that, as CAM shut down, it actually shut down in a rather dramatic way. So it didn't just stop suddenly, but it first sort of had this margin 1, which you see in blue, and I had relatively slow flow, relatively steady flow everywhere. And then it suddenly shifted to a new margin, which is the margin 2 in red. Now let's think for a minute just how surprising that is, right? Like in the sort of at the resolution of the data, which I have here, this margin jumped, right? Like it just kind of discontinuously went from one location to another location with any sort of transition in between. And these are like, those are like 30 kilometers. That's a huge change, which is, I think, at first counterintuitive when you think of viscous fluids as sort of moving slowly. But of course, you can also think of viscous fluids as instantaneous stress transition, right? And when you think of it that way, it suddenly makes a bit more sense where the ice stream is just adjusting to what happens underneath in the subsurface. And that adjustment is instantaneous because the stresses get transferred in an instantaneous way. In addition, we also see data, or we see indication of a potential meltwater channel being generated. That again is actually observations, and it comes from the fact that a channel carves out a cavity. So the ice, when that cavity, when there's no longer flow in that channel, the ice dips downward. So you can see that these sort of indications of channels through a dip in the surface ice. So let's compare this to our model. So suppose here we did change the routing of the water such that you have a channel first in one location and then in the other. What would happen is that the shear strength at the bed suddenly changes at the time scale of water. So over weeks, over months, I suddenly have a fundamental change in the basal strength. And with that comes a jump in the margin. So on top, you first see the blue margin, and then you see the jump. So that's, let me play that again. Maybe it was a bit quick. So you see the blue margin here disappears, and then the ice stream overshoots a little bit. It comes back and creates this new margin at this new location in an almost instantaneous way, which I think is at least an indication that, you know, like some of these thoughts are reasonable. Obviously, we don't know where those channels formed 300 years ago when this all happened. But at least I think it is a physical mechanism with which we could explain this very sudden rearrangement. So what's the bottom line here? The bottom line here is that ice streams have different force balances, and different things are important at different stages. So if I'm upstream, if I'm sort of closer to the continental divide, to the center of West Antarctica, I might have a distributed water film, and I might have sliding of the ice that is stabilized by freezing in the ridges. However, if the ice stream speeds up too much, I'm creating too much heat in these margins, and that weakens that weakens the force balance, so that weakens the lateral stresses, which balance the other two stress contributors. And then I can have a stable margin because the water that's created in the margin stabilizes the margin. So if I have an increase in width, more water is created, which drains more water from the remaining sediments, which stabilizes the margin and pushes it back. On the other hand, if it goes the other way, I stop producing that much water, and then the base gets a little weaker. So here I have a stable fixed point where I can actually create a relatively steady margin position, which is something that we do see in Antarctica. We do see instability, but we also see a lot of stability. Most of the ice streams are actually seemingly quite stable. And then if we have more and more water, you get to this sort of distributed cavity world, which I think is reasonable as sort of a dynamic regime for CAM, where you have so much water in different patches that you can just kind of jump back and forth between these, right? So like the basal strength distribution is no longer one clear bump, but it has a lot of little bumps. And so I can jump from bump to bump depending on what the water does. But the bottom line here is that it's the water that runs this show, right? Like, so this ice stream would change behavior based on what the water does, which then helps us answer our question that we started with, which is, can ice stream locations and widths change on a decadal time scale? Yes, probably even a yearly time scale, because water reroutes no problem in days or weeks. So this can be really rapid, which is a touch concerning. Most ice sheet models currently assume that the ice streams will just stay where they are forever. But that assumption is often just made for simplicity. It's not like we actually have a good reason to expect that. And this kind of analysis would suggest it might not be true. So then that's nice. But the other question is, CAM is kind of a funky case, right? Like, this is just one ice stream out of many, and it died, and who knows, like what was going on with CAM. So are these readjustments really likely? Are they likely going to lead to rapidly increasing sea level, right? Like, our goal here was not only fundamental understanding. We kind of tried to create that along the way. But what we really want is we want to understand sea level rise. So are these readjustments likely going to happen? And if you ask that question, you would need to look at a different part of Antarctica, which is called the Amundsen Sea. So if you thought Antarctica was weird by now, it actually just getting weirder. So here on this plot, you see the little red dots and the blue dots. And this area that I talked about before, sort of the Suckale coast, that actually has a blue dot. It's actually gaining mass at the moment. And the reason it is gaining mass is because Can died, or at least that's sort of the current thinking, that that is one of the reasons that this area is gaining mass. If you're interested in mass loss at the moment, it's really all happening in the Amundsen Sea sector, where two glaciers, Pine Island and Thwaites Glacier, appear to be disintegrating rather rapidly. And that's the topic of a huge field campaign that's currently going on, that I'm a part of, funded by the NSF and that many groups work in, where we try to get to that glacier. We try to get better data for that glacier to answer the question whether this glacier might actually disintegrate, which is different from asking whether there is a possibility of disintegration, which yes, there is. It's nature, it's complicated. There's always a possibility of a mess being created, but that doesn't mean it's gonna happen. So let's think a little bit about Thwaites. Now, Thwaites is shown here. It's a much more complicated glacier than the area we just looked at. For one, it has very complicated topography. So here you see sort of similar cross sections through this fast flowing zone at 1, 2, and 3. And you can see, like, you know, this is not plug flow anymore. This is not a flat surface anymore. You know, this gets rather complicated. Also, take a look at the speed plots in the middle here. The classical ice stream force balance would give you one speed in the stream and one speed in the ridges, which is true on the Suckale coast, but here, far from it, right? So like the first thing we need a different model. We need model 4.0. And here is model 4.0 that my grad student Paul Sommer is working on. So this is still a free boundary model because we really want to understand the dynamics of these margins. But now we have a body fitted mesh, we have hard rock in the subsurface, we have sediment in the subsurface. So it gets a little bit more complicated, but the basic idea is really just the same. It's also been benchmarked and we looked at all of that. So how can we use a model this complicated to come up with testable field predictions, right? Like the issue is always, can you still test your model? And so our approach to that was, again, sticking with the forward modeling philosophy. We have a couple of candidates that we think can mess with the basal stress. And those candidates are essentially shown here. One is overburden. It's just the weight of the ice. The weight of the ice matters because it creates a huge pressure in the water system underneath. And so overburden stresses, which vary quite a bit in this area where you have this much topography, could be important. Then it could be hydrology, right? Like that was sort of the key driver, I think, for our Suckale coast models. Is sort of really a lot of this variability that we see comes from variability in hydrology. So that's still the case. And then we have geology. Geology in this case really refers to the rock versus the sediments, right? Like rock and sediments are very different. Sediments have this approximately plastic behavior, which is highly nonlinear, where they basically go from locking to just sliding with very little in between. But the rock is very different, right? Like the rock is never going to disintegrate. So the rock is going to give you a very different sliding law. So what we did here was, assuming that each of these three processes is dominant, what is the kind of basal strength distribution I would assume to come out of this? And how well does that match the surface velocity? So we're trying to forward compute the surface velocity field to then get some sense of like, what is the explanatory potential of each of these three processes? So on the left, you see the observed data. So the 2018 observation is the speed, the distribution of speeds we saw in 2018. And on the bottom, you see these predicted flow fields. And you can immediately identify that hydrology seems to be doing quite a bit better than the other two, which to me suggests that hydrology is a strong candidate for the process that might dominate the basal strength at Thwaites. Now, what does that mean? That means that actually Thwaites Glacier might change its slip patch, right? So that's what we show here. If we then run our model forward in time. And the key thing that is changing here is the mass of the glacier. So what's really changing in this case is not the water. We keep the water fixed in these simulations. What we change here is the weight of the overlying ice because Thwaites is currently thinning very rapidly. So the more it thins, the less gravitational driving I have, which means that, you know, I'll have to readjust, or the glacier has to readjust its slip area. So you can see that our models would suggest that 25 years from now, 50 years from now, we actually see a shrinking of the current slip area. Now, existing models neglect that possibility. Existing models always assume, because they take a flow point of view and they don't take into account slip patch dynamics, that the sliding area stays the same, stays at the same location, same width, same general behavior. And then I get sort of issues like the marine ice sheet instability, where this kind of glacier ultimately just sort of starts disintegrating completely. That being said, if the slip area does adjust, as our model would suggest it could, because I'm actually reducing the driving stress, so I'm reducing the degree to which I force this motion, then I would start seeing this glacier break up. So that's kind of similar to the CAM case, which shut down entirely. Our models would suggest that we should see Thwaites Glacier breaking up and developing these new shear margins that were not necessarily there before. Now, of course, that's a prediction that we need to, test against data. Unfortunately, with this kind of model, because it is looking at pretty fast time scales, you could actually test this. I mean, at least within, like, say, 10 years, you could see some deviations between nature and the model occurring. But for now, we don't know whether this is true or not. It's just an idea, and it's just sort of using our thoughts for the Cycle Coast and applying that to Thwaites Glacier. And I guess my current thinking on this is that I don't think there's necessarily going to be as much sea level rise from Thwaites as we thought as models would suggest that completely neglect slip patch dynamics and free boundary dynamics here. However, our model assumes constant basal conditions, like that's what we just used in the previous slide to sort of predict this rearrangement of the slip patch. But is that true, right? Like, I just convinced you, hopefully, for the Cycle Coast that, the basal conditions may change, right? So that's probably not okay. And here you see some data on that. So for example, here you see the relation or an overview of different papers arguing for different amount of water increases leading to a slip increase. So for example, for Greenland on the left, some papers have argued that more increase of water or increase of basal water can lead to a 25% increase. Just a few kilometers away, other papers have argued for a 220% increase. So there's a huge amount of variability. In Antarctica, some people have said there's barely any effect of the water, but in other places, there's much bigger effect, right? So basically the data is all over the place. And why is that? It, again, is, of course, because the sediments are much more dynamic than we commonly give them credit for, right? Like, so how does this basal interface look like? Here you see a photo where you see sort of all of these fine slip lines developing, right? So this is a very complicated interface, and the sediments are a crucial and important dynamic part of it. And that's something we see a lot in paleo data, right? Like, we need data, and I think paleo data is a really strong contender. We can also take advantage of advances in laboratory experiments and granular mechanics, which have shown that I can think of the slip behavior as a phase transition, right? So like the sediments actually undergo a phase transition that is governed by an order parameter called fluidity as it approaches slip. Now, why does that matter? It matters because when I try to simulate the interplay between water and sediment, right? Like, the question about basal strength is really a question about the interplay between water and sediment. So here we're writing a new model, which is our model 5.0, in which we're trying to understand, okay, for these different slip dynamics, right? So for example, for Thwaites, I could go to a place where I'm currently driving the sediment deformation through a rapid speed to one where the lateral margins dominate the behavior, right? Like, how would that affect the basal strength? How would that affect the bed? That's something we can look at with a very simple model. So here we're just trying to isolate that part. And we can look at these two end members, stress controlled and rate controlled, right? Like, where one would be sort of Thwaites in the past and one would be Thwaites in the future. And what this kind of model would predict, and the key outcome of this model, without going into all of the details here, is that in one of these, I'm basically moving the slip zone, like the slip interface, into the sediments, right? So like the water that comes in, and we have a lot of water coming in underneath Thwaites, could move the slip interface deep into the sediment layer. And what that means is that I'm now transporting not only the ice, but actually a huge amount of the sediment layer. And I start building up landforms, which then again would change completely the dynamics of this feature. So in one scenario, in the scenario where I have the slip zone shifting into the sediments, I see deep slip and I see it in the sediment, and I see bed form evolution, which could lead to further stabilization. And in the other one, I just see sort of sediments being shaved off at the surface, right? So like all of the sediment transport happens at the slip interface, and the slip actually happens between the ice and the sediment, not within the ice. So again, these are two very fundamentally different dynamic regimes. Have these been seen before? In Antarctica, it's hard to tell. We do see these very dramatic bed forms, which suggests that there can be a huge difference in sediment transport. But here is a simpler and more easily observed example where I have Black Rapids Glacier and the same Black Rapids Glacier a few years later. There were two field campaigns at this glacier. One argued that the slip interface is very shallow, so in the upper 20 centimeters. That was in 2002. But the older field campaign had argued that it is deeper than 2 meters. They couldn't know how much deeper because that's where their data ended. And that's what our model would confirm if you have rapid variation in water influx, that you can shift the position of this interface. So bottom line here is it justifiable to assume basic conditions remain constant? No, right? Like spatial and temporal variability is high, particularly when I'm approaching instability, when sort of if Thwaites Glacier is indeed approaching instability, things can change in a very profound way. So that's hard, right? Like, so what's the bottom line here, right? Like, so what do I do with that? On the one hand side, I have this huge uncertainty regarding ice stream locations and width. I know that can readjust, but I don't necessarily think it's going to happen. And I'm also not sure about the base, and it's a mess. And like, what the heck? Like, what do I do with that? Right. And I think, to me, the key insight really here is the uncertainty is huge. It's just inherent to the dynamics of the system. It's a very deeply coupled nonlinear system. There's always going to be uncertainty here. But I also think that this uncertainty in itself might actually be the single most important scientific contribution of this whole field for planning. And I think we can use this uncertainty in our planning in a more intentional and meaningful way. So just sort of as a quick taste towards the end, what does that mean in particular? How can we make this uncertainty in near-term sea level rise actionable? I very much doubt that it's going to go away. But like, who knows, right? But I think it's not going to go away because it's inherent to the system dynamics. So what can we do with it? I think the first takeaway is I think we need to think more about adaptive solutions. In the past, flood risk management has very much relied on historic data and just kind of saying, this is the return periods of floods. Let's prepare against this flood. Now we are in a world where things are rapidly changing. And I think we need adaptive solutions. And if we don't have that, it might backfire. So here's an example of that. Here is a flood that happened in the Bay Area in 2017. And this flood happened not because of a huge extreme, but it happened because of accumulation and rainfall in a reservoir that then overran. So what you see on the bottom left is the reservoir overspilling. Why does the reservoir overspill? Because it is adjusted to a precipitation data that is old, that is pre-1970s, but the variability in precipitation has gone up hugely. So now we're looking at much more variability, and in wet winters, the reservoir will overspill and create huge floods. So you can see that all of these past overspill events are actually just related to the accumulation of rain in the reservoir. So we need to manage these things differently, right? It's like these overspill floods are not driven by extreme events. They're just driven by cumulative precipitation. And it highlights how a single wall height can be tricky if you have a hazard that changes over time. The second piece is, I think, the need for equitable solutions. I often hear from the stakeholders we work with, oh, we need better predictions of sea level rise to do anything. I don't think so. Certainly in the Bay Area, we know where flooding is going to happen. And it so happens, for example, in our backyard, that a lot of that flooding is going to hit communities that are socioeconomically disadvantaged. So on the bottom line, on the bottom left here, you can see the percent of households that are currently at risk of severe flood damage, so severe that it would eat up more than their household and more than their reserves and more than their savings. So these are financially unstable households. You can see that, for example, in the darker brown areas, which is our neighboring community, East Palo Alto, you have about 50% of households that are so on the verge, that are already on the verge of financial bankruptcy, and they cannot cover additional flood costs. And on the right-hand side, you see how that would increase, with certain communities increasing dramatically in their financial instability. And then the third, I think, is we need to think about this more regionally. So this is another study we did in which we looked at traffic disruptions. Our stakeholders sometimes like to think that, oh, if I'm not in the flood zone, I don't have a problem. But of course, that's not true, because if you're part of an urban area, you will be affected by what happens in that urban area. So here we showed in this study that the communities that are most affected by travel time delays arising from flooded roads are actually not the ones in the flood zones, but are the ones that have the fewest alternative roads. So that got recently published in the Science Advances. You can see here on the left, the North Bay is the one that's going to have a problem, despite the fact that most of the flooding is actually happening in the South Bay. So we need to be thinking more about the consequences of these events. So let me wrap up. What's our conclusion? The causes and consequences of uncertainty in near-term sea level rise. Rapid changes in land ice dynamics is driven by potentially rapid change at the interface of the ice sheet. It's not inherent to the system dynamics. It's really in boundary dynamics, right? So that's the ice-ocean interface, but it's also the basal interface. So as you can see from, like the Stokes equation being an elliptic equation, this is a boundary value problem. So most of the dynamics comes from the boundary. 2, existing models for quantifying sea level rise do not contain the processes that actually govern the temporal and spatial variability of ice loss, right? So they don't have the water, they don't have the sediments, they don't have the margin dynamics. They're not free boundary models typically, right? So all of these models will add more uncertainty, not less. The large uncertainty associated with estimates of sea level rise in the near future is in itself an actionable insight. And I think it's really important for us that we think about how we can explain that and make that make so the consequences, have a discussion about the consequences of this uncertainty, which I think in many ways contradicts with how we've been managing flood risk in the past. So I think it is really important, and it is a really important and meaningful scientific result to have this uncertainty, be able to estimate that. With that, I would like to end on one of my favorite quotes. Everything should be made as simple as possible, but not simpler, by Einstein, who thought a lot about modeling, just like we do, and just like I hope you guys all do. So hopefully there's some questions.
Yeah, thank you very much. And could everyone unmute for a second and give Dr. Suckale a round of applause? That was really great talk. Yeah. I had, I'm not, personally, I don't work as much in this field, and so it's fascinating to me to see how complex this whole situation is. Maybe I'll start with a question more of a thinking from a big picture significance point of view. When you're developing these subsequent versions of the models, and I think it was version 4 where you were talking about introducing modeling the slip patches, and you had projections out for what might happen in 25 or 50 years. Along with it, do you have a sense of as new data comes in, how you might be able to exploit differences between your data and your model projections to try and give you a decent estimate of what the uncertainty will ultimately be in the sea level rise? Like maybe, and how significant is that version of the model over simpler versions, earlier versions of the model that don't incorporate those slip patches?
Right. Yeah, that's a great question. So I think, one of the quote unquote issues with the ice sheet models, right, is that they're really meant to talk to very large scale data. These guys were developed when we first got the remote sensing data that triggered this whole debate about ice sheet dynamics, right? So they talk to that data. They have testable predictions against that data. But now we have all of these field campaigns going out, right, and measuring the details of the subsurface and the shear margins and all of this. These really large models are very difficult to test against that field data because they don't have, their grid size is like 10 kilometers, right? Like they don't have anything below that. So a big motivation for us is always to we often write models for the sole purpose to be able to be testable against a new set of data. Mm-hmm. Right? Because Antarctica is so underobserved. Like we have for Thwaites prior to this campaign, we have literally no field data, nothing to test against, right? So it's very difficult to really come up with detailed models, right? So one of the things I'm most excited about when it comes to being part of this field campaign is we now develop this data, particularly sort of, I need a model that is testable against new seismic data. I need a model that is testable against new hydrological data, that is testable against these sort of bottom drilling data sets for like sediment sizes and all of that, right? Mm-hmm. So a big motivation here for us is always to intentionally develop models that kind of look at different processes, but also models that can be tested against data and new data sources as they come in, because these data sources are so precious. We need to make the most out of them. And I think models can go a long way towards making that happen.
Okay, awesome, very cool. Niels, I see you have your hand raised.
Hi, so Jenny, nice talk, very interesting, something I haven't really thought of before now. So I have a suggestion maybe, and then you can tell me why it's either naive or wrong. Mm-hmm. I guess one thing I'm hearing from you is that a lot of the uncertainty comes from what the dynamics is at the boundary of the basal layer and ice sheet, and in fact even where the slip boundary is. So what I'm thinking might be useful is, irrespective of where this boundary is, maybe it's the case that climate change affects each one of these types of boundaries in the same direction. So, I mean, naively, I'm thinking that you have global warming, so you're generally going to have more water around, and the water is somehow going to filter down to this layer, and then you'll get more slippage, irrespective of whether the slippage is occurring in between ice and sediment or sediment and basal rock. Is that
right? Yeah. So that's, I think, an idea that the community has thought about for some time now. And so can you still see the slide? So this is basically the essence of this slide, right? Like, it's less so the case for Antarctica, because keep in mind the average annual temperature in Antarctica is minus 26 degrees. Right, so like it really doesn't get very warm in Antarctica ever. So surface water, we barely have any surface water in Antarctica that would filter down, not even with climate change, not even if you increase by 2 degrees, you're still well into the frozen regime, with the potential exception of the Antarctic Peninsula, which is sort of the very top of sort of the elephant trunk here. But most of Antarctica stays cold enough usually to not have ice coming from the top. All of the ice, not have water coming from the top, all of the water really comes from the bottom, right? So Antarctica is sort of one end member of this. For Greenland, this whole argument is a lot more interesting. So for a long time, people have tried to, primarily from an observational point of view, try to identify the relationship between seasonal meltwater influxes and speed. And that is, for example, the Swally paper and the Bartholomew paper you see here have sort of estimated some of those increases. The problem is some glaciers actually slow down when you pump water into them. Some speed up by like 2-3 orders of magnitude. Some speed up by a factor of 2. So bottom line is, it's not that simple. So we haven't really been able to identify a clear correlation there. There's now a classification of Greenland glaciers with like, I think 3 or 4 classes, which argue that some are prone to seasonal influxes and some are not. The problem is it also varies year by year. So in other words, it's messy. And I think it comes down to the hydrology at the base really being a lot more varied, than just a thin film, right? Like, I can't just think of this as a lubrication problem. I need to think of this more deeply. So sometimes, sometimes the slip depth might change. Sometimes the routing of the water might change by going from a film to a channel. And sometimes, the water, the glacier might not be that dependent on the water because it's mostly held on the edges, right? So unfortunately, that line of thinking hasn't been as successful for Greenland as you would think it is. And I think it's a testimony to the profound nonlinearities in this system, right? Like, it's very coupled, like the sediment and the water and the ice, they all talk to each other. And there's just a variety of dynamic regimes that can come out of it. And it's not always as sort of, it's hard to sort of identify one single mode of behavior. It's really a range of different behaviors that kicks in.
Okay, thanks.
Well, and I see Nick, you've raised your hand. Would you like to ask your question?
Yeah, I was just wondering is it a normal process over a long time, like thousands of years, for Antarctic ice to slip into the ocean, or is it more of a recent process driven by global warming?
It's very common, right? Like, for example, when we looked at, like the data that looked at CAM, right? Like all of the data that looks at sort of the Cycle Coast, most of that thinks about the past, right? Like prior to climate change, 200, 300 years ago. So this pattern that you see here, for example, right? Like this behavior that Antarctica melts from the inside out rather than from the outside in, that is definitely pre-climate change. We see that in old glaciations. We see that even for like, at least it's been inferred to be comparable to past ice ages. So the current thinking is that the general mode of behavior of Antarctica is kind of quite similar to what it used to be prior to climate change. The key question is, how is climate change going to change all of this, right? Like, and that's really difficult to know because it's already a very coupled and nonlinear system. So for example, the CAM shutdown had nothing to do with climate change, right? Like that was well prior to climate change. It was just sort of the rearrangement of water that happens, that kind of can happen naturally, right? Like, so for example, the current thinking is that one of the neighboring ice streams basically rerouted some of that water, that the perturbation in the neighboring ice stream rerouted some of that water and basically stole that water from CAM. The Amundsen Sea, I think it's quite clear that climate change plays a role there. The way that climate change comes in from Antarctica is really at the ice-ocean interface, right? Like that's really the key coupling, because the ocean is warming quite a bit, and it's warming primarily in the Amundsen Sea, and then sort of it's projected to go around the Antarctic Peninsula and into the Ross Ice Shelf, which is sort of on the other side of the Cycle Coast, across sort of the other side of West Antarctica. So if you temper with that interface, right, like if you sort of mess with that ice-ocean interface, the question that really we're asking here is, if you mess with the ice-ocean interface, what is happening to the land ice, right? Because the sea level rise contribution all comes down to the land ice, but the ice-ocean interface is kind of the way you kick it, right? Like the ice-ocean interface basically is the way you perturb the land ice. The question is, how is the land ice going to respond to that? Because the land ice hasn't really seen perturbations of the magnitude that we're currently seeing in terms of ocean temperatures in the observed record. We have no data on that. We can only speculate about what might happen. And some models sort of have focused on the possibility of instability, which is good, but the possibility of instability isn't, necessarily saying that the instability can happen, right? Like many sort of natural systems have sort of positive and feedback loops, and one kicks in after the other. So that's really, I guess, the piece that we're struggling with is, overall, I think the dynamics of the ice sheet hasn't changed much, right? Sort of pre versus post climate change. But the question is, how is it going to evolve? And also keep in mind, Antarctica has a sea level rise equivalent of 60 meters, right? So that's huge. And we care about even like a half meter would be huge news for the Bay Area, right? Like to have a reliable prediction, I need to get this right to basically a 1% error. Now that's hard, right? Like that's hard for any system, let alone a really complex, deeply coupled nonlinear system. So I think that's the challenge we run up against, is that what we need is a degree of accuracy that would require a depth of understanding that I think is far from where we're at.
Awesome, thanks. And I just want to check, Niels, did you have another question, or your hand still raised from before?
I do have another question.
Okay, great. And maybe we'll take Niels' question, and then after that we can let people go to their next meeting. But go ahead, Niels.
Okay. Actually, what your answer to the previous question made excited another question in me. But let me ask the other question I had. I'm having some understanding of what's actually happening. I'm having continuity equation problems. That you're like the picture you're showing right now shows like 1,000 meters per year flow rates on large portions of the coastline, and so to me, if you have 1,000, if you have a flow which is 1,000 times larger in one location than it is upstream, then that's something that requires explanation. So either you've got to have the cross-sectional area through which the the flow is flowing, and it decreases by a factor of 1,000, which, I mean, it looks just the opposite to me, the way the picture looks.
Right.
Or you've got to have like a huge amount of snowfall, or or it's got to be, it's not a steady state. I mean, so which one of these things is, or is it all some combination of them?
Yeah. So the thickness of the ice doesn't change hugely across Antarctica, right? Like, so the thickness of the ice is reasonably constant. One thing that is very variable is the snowfall. So the snowfall really does come almost exclusively onto the continental divide, which is basically the center of West Antarctica, right? So that's one piece. So the snowfall definitely adds a lot of variability spatially to where the flow is happening. So the snowfall primarily occurs in the center, and the loss of mass primarily occurs on the ocean edges, right? Also note that, for example, particularly if you look at the Ross ice shelf, which is sort of the one on the other side of the Suckale coast, a good share of that is actually draining East Antarctica. So there's a lot of sort of the connection, the dynamic connection between East Antarctica and West Antarctica is also a very important one. So maybe just sort of as a fun thing to remember, if you have troubles picturing Antarctica, you can just pick sort of your left hand, and that's about the topography of Antarctica, where East Antarctica is basically a mountain range. It lies very high. It's well above sea level, but West Antarctica is below sea level, like a fair chunk of it anyways. And then you have the Antarctic Peninsula sticking out. So like some part, and East Antarctica has a much thicker ice pack. And so you can see from the tributaries to the Ross Ice Shelf that you start draining part of East Antarctica already, but also I think like the snowfall is very variable. But the other thing is, the different drainage areas are also coupled, right? So for example, the Ross, the Suckale coast is building mass despite the fact that you have these rapid drainage zones, because you just had way more drainage zones, say 500 years ago. So it's the mass balance, and I think that justifies why we have so many models looking at the mass balance here. The mass balance is quite delicate, but I think it's also very limited by data, because we actually don't have very good data on where snowfall occurs and to which degree it varies. It definitely varies spatially, it also varies temporally. It's difficult to quantify where exactly the snowfall is happening, and also how that would change with climate change. So the snowfall is definitely a huge uncertainty here, which then again comes to the coupling between the atmosphere and the ice, right? Which is also a big open question. But the Antarctica is not in a steady state. I wouldn't describe it as such, right? Like, so we are losing ice from Antarctica. So Antarctica is currently losing mass, which then goes into the question of the glacial cycles, right? Like, that wasn't always true, right? Like, Antarctica also had phases where it was growing. But that kind of then happens on a very different time scale. So those are more like millennia type dynamics. Does that roughly make sense? It's it gets complicated, but I wouldn't think of Antarctica as a steady state.
Okay, yeah. All right, thank you.
Well, thanks so much. I know we've gone over a little bit, but we appreciate your extra time in answering all these questions. And this is a really fascinating talk. So those who are still around, could you unmute one more time and give Dr. Suckale a great round of applause. Thanks.
Thank you. My pleasure.
Awesome. Thank you. All right. You have your hand raised again, Niels. You want to ask? I'll stop the recording.